Now it is time for Mod 5, acids and bases and oxidation and reduction. So let's start out by talking a little bit about acids and bases. Acids taste sour, so what are some things that taste sour? Vinegar. Vinegar tastes sour, vinegar is an acid. When acids are combined with metals, some metals create hydrogen. There are some metals that don't. Those tend to be the expensive ones, so gold, silver, platinum do not create hydrogen when you mix them with acid, but other metals like aluminum and iron, they do create hydrogen. Acids tend to turn litmus red. Well, they do. They don't tend to. They do. They turn litmus red, and also when acids and bases react, they form salts. Bases taste bitter. So what things are bitter? Certain medicines are bitter. So when you take cold medicine, for instance, it just doesn't taste very good. That bitter taste, that's because it's basic. Bases feel slippery on skin. So soap is a base. Now, bases will feel slippery on skin, but not everything that feels slippery in the skin is a base. For instance, motor oil is not a base, but it feels slippery on your skin. So just because something's slippery doesn't mean it's a base, but bases will feel slippery on your skin. Bases turn litmus blue, and they also make salts. So let's start with the simplest theory. Arrhenius theory says that when you throw an acid into water, it forms hydronium ion. And here are some common acids here. This is a very big one, sulfuric acid. Sulfuric acid, also known as battery acid, we use this quite a bit, and the biggest use for acids and bases that you'll find is for fertilizer, making fertilizers. Nitric acid is also a very strong acid. Strong acids, we'll learn later, mean they dissociate, and this is used to make fertilizers and explosives. Hydrochloric acid, same thing, use it for cleaning. This is also known as muriatic acid. Phosphoric acid, it's a weak acid. It's not as powerful as the other acids, used for fertilizer mostly. Hydrogen sulfate ion, this is used for cleaner. Lactic acid, we have this in our muscles, so when we lift weights or run or whatever and feel a burn, a lot of that's from lactic acid. Also used when things spoil, or like for yogurt, for instance, the lactic acid forms. Acetic acid, this is vinegar. Carbonic acid, this is found in soda water. Boric acid, this is used for soap, for borax soap. Hydrocyanic acid, this is used for some plastics. This is HCN is also very toxic. Now, along with Arrhenius theory, a base is something that forms hydroxide in water. So acid forms hydronium, H3O+, base forms hydroxide, OH-. So let's talk about the different ones. Sodium hydroxide, also known as lye, used for soap and other sorts of acid neutralization reactions. Same thing with potassium hydroxide, also for soaps. Both sodium and potassium hydroxides, sometimes those are used in drain cleaners too, so really powerful industrial strength drain cleaners will have these in them. Lithium hydroxide, used for storage batteries. So is potassium hydroxide used for that as well. Calcium hydroxide is used in cement, so that's the primary use for that. You take lime, which is calcium oxide, you make it wet, it makes calcium hydroxide. It absorbs carbon dioxide from the atmosphere to form calcium carbonate. That's why people yell at you, like kids, when they start putting their hands in cement, because if they put hands in cement and rub eyes, you can damage your eyes and blind yourself. Magnesium hydroxide, this is a laxative, an acid. It's both an antacid and a laxative. So certain calcium carbonate is also used as an antacid, but tends to make people constipated. Magnesium hydroxide is also a laxative. Ammonia, used as a fertilizer and as a cleaner. Hydroxide and hydronium. So water, H2O, but H3O+, an extra hydrogen, has an extra positive charge. OH- has one less. has a negative charge. And that's in general what acids and bases do. Acids tend to add positive charge to things. Bases add negative charge to things. And we'll learn later about about biochemistry. Most biological things have a negative surface. And that's why adding a base makes your skin feel slippery, because adding negative charge to something that's already negative makes it bigger, blows it up. And if you add acid to biological things, it makes them shrink. And when it blows up and has that negative charge, it feels kind of slippery to us humans. And there's another theory, Bronsted-Lowry theory of acids and bases. This states an acid is a proton donor. So the hydronium ion, H3O+, will, or whatever the acid is, either gives a proton to hydronium, or hydronium then gives the proton to something else. And then the base is a proton acceptor, so it gets an extra proton. So this illustrates this. This is the acid. It gives a proton to the base. That's the Bronsted-Lowry theory right there. And some acids and bases are stronger than others. So acids and bases that fully ionize, meaning they break apart, meaning they're strong electrolytes. These are strong acids. So here are the strong acids, and here are the strong bases. Everything else is a weak acid or weak base. I know in the previous slide we had calcium hydroxide and magnesium hydroxide as strong bases, but they're not really. You can eat magnesium hydroxide and you'll be fine. If you eat sodium hydroxide, you're going to be going to the hospital. And then when acids and bases combine, they form salts. So remember, an acid tastes sour and a base tastes bitter. What does salt taste like? It tastes salty, right? It doesn't taste either of those. So, and I remember our taste is a chemical sense, and so that way you know that salts are chemically different than acids and bases. Water also slightly self-dissociates, very slightly. So we talked about these. The acids and bases, so here, these are strong acids and strong bases. These are very dangerous, especially at high concentrations. And weak acids and bases, they're not very corrosive. They can still be dangerous. Acetic acid, for instance, in its pure form, will give you blisters, but they're not. And ammonia hydroxide in its pure form, it can knock you out. But these are not nearly as bad. You can touch pure lime with your hands. I mean, it's not recommended, but it's not going to be nearly as bad as if you touch pure lye. If you touch pure lye, you're going to be hurting pretty badly. And anhydride, so an means without, hydride means without water. So anhydride is something without water. And so nonmetal oxides are acidic anhydrides. So sulfur trioxide plus water makes H2SO4, sulfuric acid. And that's also how acid rain forms. And metal oxides are basic anhydrides, same idea. So this is, I told you about this, lime plus water makes calcium hydroxide. And here's the neutralization reaction. Base and acids combine to form salt and water. And now the salt has different chemical properties than the acid and the base. Now I'm going to talk about pH next, but I want to do a review for logarithms. So 10 to some power, that power, that x, is the log. So which means if you take, a log is the inverse of a power. So the log of 10 to the x equals x. So remember, if for 10 squared means 10 times 10 or 100. So the log of 100 is 2. Likewise, log of 1,000 or 10 times 10 times 10 or 10 cubed is 3. And then to review how the negative logs work, 100th is 1 over 10 times 1 over 10, so 1 over 100, which is 10 to the minus 2, so the log of 100th is minus 2. And now, let's talk about the pH scale. pH scale means power of hydrogen, and it's a logarithmic scale. And what I mean by logarithmic scale, That means when you go up a pH unit, you actually go up by a factor of 10. This is sort of like the sound scale, decibels, or the Richter scale. Going from a magnitude 6 to a magnitude 9 earthquake is a very big deal. Every single step in the Richter scale increases the energy by a factor of about 32. So going from 6 to 9, that's about 30,000 times stronger. And likewise for decibels, every 10 units in a decibel scale means the sound increased 10 times. So the logarithm is the same thing. And I'll show you this as we go along. And also buffers. Buffers are certain substances that do not change much with their pH value. And that's important because we have them in our blood. So here's the pH scale. And this is logarithmic, so that means when you go from pH 0 to 1, the concentration drops by a factor of 10. But look at it this way, if you go from pH of 6 to a pH of 3, you think that you only double your concentration, but you actually go up by 10 to the third or 1,000. So every step is a factor of 10. So be careful with that with pHs. So what's the pH of a 0.001 molar solution? So if you go to the previous slide, this is 10 to the minus 3, and then the answer is 3. So here you can see that the answer is 3. So from before, anything greater than 7 is a base. Anything less than 7 is acidic. Pure water, actually this is not even really true. Here on Earth, there doesn't exist pure water because of the atmosphere. Pure water on Earth has a pH of about 5.6. But there are certain things that are naturally acidic. Urine is naturally acidic. Tomato juice, all like the citric stuff, these are all acidic. And then blood, slightly alkaline. Alkaline is another word for basic, but mostly neutral. Baking soda. Ocean water has a variable pH, slightly alkaline. This is magnesium hydroxide, is milk and magnesia. So these things are alkaline. So here's some common things here that are that have certain pH values. I talked about buffers. Buffers are something that resist a change in pH. So vinegar has a pH of about 3, and if you touch vinegar with a cut on your hand, that you would think that would be really dangerous because vinegar is relatively acidic and then it would make my blood acidic. Well, it turns out that in our blood we have a buffer. So that means that if a little bit of acid, like lactic acid from our muscles or some of our stomach may bleed and get hydrochloric acid into our bloodstream, that will be absorbed by the blood. And so it takes a lot of acid or a lot of base to really get us to injure us in terms of our blood. And that's why we have our buffers. And the buffers do a really good job of maintaining our pH. This is important because if our blood pH changes, this can cause organ failure. Or it will. It just depends on a matter of time and if you catch it. That's why when you watch shows like ER or House, when people start to crash, they crash fast. Why? Well, because their blood pH is kind of starting going off, and then that can cause organ failure. And specifically the organs that regulate pH are our lungs and our kidneys. And they mostly regulate by getting rid of acid. So we get rid of acid in our lungs by exhaling, because carbonic acid in our blood, when you exhale carbon dioxide, that will make our pH, blood pH, go up when you exhale. And the same thing with peeing. When you urinate, you remove acid ions, so that makes your blood pH also go up. But how do you get your blood pH to go down? It's real simple. Hold your breath. Hold your breath, your blood pH, your blood will start to become more acidic. And so if you ever see people trying to sell you things like alkaline water, it's a bad idea. If you need to drink alkaline water to regulate your pH, then you should really be on kidney dialysis, because it means that either your lungs are damaged, as long as your lungs and your kidneys are working fine, there is no need to take any sort of alkaline water. Acid rain, anything that has rainwater that has a pH below 5.6, that's acid rain. And certain air pollutants, which we'll cover later, turn into sulfuric acid and nitric acid in the air, and then by rainwater have acidic rain. This dissolves calcium carbonate, so marble and limestone can cause damage to our architecture. It can also damage metals, and also tends to acidify the soil and groundwater. And Hawaii actually has really terrible acid rain because we have a very huge polluter close by. It's the volcano. The volcano produces, the gases from the volcano produce really terrible acid rain. That's why if you go to a graveyard here in Hawaii and you look at the gravestones, they're all corroded because of the terrible acid rain that we have. So what do we use acids and bases for? So what? Why do we care? Most of them are from synthetic fertilizers. So we use acids and bases to make fertilizers. And we'll cover later in agriculture that if we tried to raise crops organically, meaning without synthetic fertilizers and pesticides, the human population of the earth couldn't be much more than 2 or 3 billion people. With the 7 or so billion people we have here on earth, it's because of our industry. And part of that is acids and bases and fertilizer. Lime is also added to calcium hydroxide. It's added to sweeten soil. Sweeten means it makes it more alkaline. Also used for petroleum and acids. Petroleum's metallurgy to make things like nitrided steel, plastics, explosives, these types of things. Bases can also be used to make explosives. Soap is used. Refrigerant. So ammonia is used oftentimes as a refrigerant to make polymers and so on. So it's not just fertilizers, but fertilizers is the vast majority of their usage, on the order of 3/4. So we're going to change topics, and we're going to talk about oxidation and reduction. Oxidation means a gain of oxygen, and reduction is the opposite of oxidation. So if something gains oxygen, reduction means losing oxygen. Likewise, oxidation means losing hydrogen, which means reduction is gaining hydrogen. And the most general definition is oxidation is when an atom or molecule loses electrons, and then reduction is when something gains electrons. And if something loses electrons, something needs to gain electrons. So because of that, oxidation and reduction reactions happen together. For instance here, sodium reacts with chlorine to form sodium chloride. Sodium loses an electron, gets oxidized, and chlorine gains electron, becomes reduced. And most biological reactions and all combustion reactions are oxidation reduction. These are very common reactions. Okay, so oxidizing and reducing agents. So I was just watching James Bond, actually, before I filmed this. I was watching Never Say Never Again, and James Bond is the agent of death, right? But James Bond never dies, right? He's Ian Fleming's character. He never dies. So oxidizing agents cause oxidation, but they themselves are reduced. Just like James Bond does the killing, but he's never killed. So oxidizing agents deliver oxidation. How do you deliver oxidation? How do you take electrons, or how do you remove electrons? You remove electrons by taking them. Oxidizing agents take electrons, therefore they're reduced. How do reducing agents deliver reduction? They deliver reduction by giving up electrons. That means that they're oxidized. So you have to think of them kind of backwards. Oxidizing agents are reduced, and reducing agents are oxidized. So remember that. And here it shows this. Here's a picture of it. Copper oxide. Copper is losing oxygen. So remember, losing oxygen is oxidation, and hydrogen is gaining. Losing oxygen. This is reduction. Hydrogen is gaining oxygen. This is oxidation. So copper oxide is reduced. It's the oxidizing agent. Hydrogen is oxidized, it's the reducing agent. So why do we care? Well, let's give a specific example. Batteries. Batteries use oxidation reduction reactions to produce electricity. And that means the anode here loses electrons and the cathode gains electrons. So the anode is oxidized and the cathode is reduced. And the other way I remember it is the anode corrodes. So the anode is going to corrode. So over time, the copper is going to go away and the silver is going to get fatter. Most batteries are not going to use copper and silver because this is kind of an expensive battery. They could, but it's not very cost effective. You're going to use other metals. So different batteries use different metals and ions. So dry cell batteries, these here, if you ever take a battery and you saw it in half, you might see something like this. You'll see a carbon rod, and if you do this, be very careful when you do it. I'm not advocating that. But you have this spongy stuff on the outside. This is zinc, and you have a carbon rod. So the zinc is the anode. When does the battery die, our batteries die? When the zinc runs out. When all the zinc corrodes away, the battery's dead. So these things are not rechargeable. In car batteries, these are also known as lead-acid batteries. These are rechargeable. But why don't we use them in our portable devices? Because they're heavy. Lead is heavy. If you picked up a car battery, it's pretty heavy. But we use them in cars and submarines, these types of applications. Here's the reaction. This is the anode, this is the cathode, lead is the anode, lead oxide is the cathode, and with sulfuric acid, also known as battery acid, forms lead sulfate and water. And then you can put electricity on the other side and the reaction will go the other way. That doesn't work for all batteries. So here shows the battery. Each one of these cells, if you take apart a car battery, and please do not do that, and if you do that, be very, very careful. Each of them has cells, so a car battery typically has 6 cells to it. Each cell is 2 volts, so each one of these cells is 2 volts, and they hook them up in the series to make 12 volts. Corrosion is a big problem. It costs the United States billions of dollars each year from corrosion. And corrosion is an oxidation reduction reaction. And iron rusting is an example. When iron oxidizing, rust is iron oxide. And let me show you how it works. So here, iron is the anode, and the rust turns out to be the cathode. And then with water, dissolved oxygen in water, iron will oxidize and form iron oxide or rust. And rust is that brown kind of flaky stuff. Aluminum doesn't rust. So you wonder, why doesn't aluminum rust? Well, you might first think that aluminum is not a very reactive metal. Turns out that aluminum is more reactive than iron. But what happens with aluminum forms a very powerful oxide layer. Aluminum oxide is also known as sapphire. So sapphire is a very hard substance. Rust is very soft and flaky. So I could rip rust off of iron with my fingernail, but I could not chip off sapphire off of with my fingernail. That's not possible. It's too hard. So chloride ions can penetrate this layer. So the aluminum oxide forms this coating of sapphire, and the coating of sapphire protects it. This is not uncommon. Titanium does the same thing. Titanium oxide protects titanium. Chloride, though, penetrates this layer, and that's why you don't see many aluminum boats, especially in the ocean. You can see them in fresh water, but aluminum boats in the ocean, that's kind of a stupid thing to do because it'll eat it away. Also, that's why I don't have aluminum parts for plumbing. And here's a sapphire, and here's aluminum foil. So why is this? Why doesn't this look blue? Why doesn't the sapphire here look blue? Because sapphire, there's iron and titanium impurities in sapphire which make it look blue. There's also other colors sapphires. If there's chromium impurities, sapphires turn red. Sapphires are actually white and kind of clear, a little bit of smoky if you see a pure one. But a red sapphire, we have another name for it. It's called a ruby. Rubies actually turn out to be sapphires. And explosions, most explosives are from oxidation reduction reactions. The exception to that rule are atomic weapons. Nuclear weapons work off of nuclear reactions, but everything else works off of oxidation reduction. So Oklahoma City, this was using fertilizer and fuel oil. So you got some common stuff that you can use to make explosives. And this is a problem because ammonium nitrate, a very common fertilizer, people buy tons of the stuff. So if a farmer buys several tons of ammonium nitrate, he doesn't really want to make a bomb, he wants to feed his crops. And fuel oil, that's very common too. So this is a difficult thing to manage in the government's point of view because they're such common things. Fire, for you pyromaniacs and firefighters out there, fire is defined as a rapid oxidation reduction reaction. So most fires that we deal with oxygen as a part of the fire, and an easy way to put out the fire is to get rid of the oxygen or the oxidizer. And oxidizing agents, by far, oxygen is the most common oxidizing agent. That's not very surprising. But ozone is also common, can be used in water purification for ozonolysis. Also, some disinfectants like bleach and benzoyl peroxide for like acne medication. So the way bleach works is it oxidizes dye molecules and it makes them look white. Actually, kind of turns it slightly blue as well. Reducing agents, what are the most common reducing agents? Fuel. Anything that's a fuel is a reducing agent. So that includes gasoline, wood, and sugar that fuels our bodies. So those are all reducing agents. And we'll talk about the thermite reaction later. That's an interesting one. Aluminum is the reducing agent. Antioxidants, so if you hear about someone say, I eat lots of antioxidants, what are antioxidants? They're reducing agents. How do antioxidants work? Why are they anti-aging? Well, let's say, for instance, you want to keep a bunch of hungry kids from eating a plate full of Brussels sprouts. If the kids are hungry enough, they're going to eat the Brussels sprouts. So how do you protect those Brussels sprouts? You put a bunch of candy in front of the Brussels sprouts. The kids will eat all the candy, they'll be too full, they won't be able to eat the Brussels sprouts. How do you keep a very reactive molecule from attacking the DNA in your cell? Well, you put a very attractive looking reducing agent like vitamin C around your DNA. The highly reactive molecule is going to attack the vitamin C and leave your DNA alone. That's how it is an anti-agent. It prevents damage to your cells by reactive molecules. And that's why you need to keep on replenishing it, because you keep on getting reactive molecules, so you need more vitamin C. Also, hydrogen can be used as a reducing agent. Well, it's accidentally many times. Hydrogen embrittlement. So this is not a problem in Hawaii, but in the mainland, especially in the colder climates, like in the northern part and New England, where it snows in the wintertime. In the old days, they used to use radiators, and radiators means hot water, so they would have a boiler room and water would boil. And they found out is that the first time that they started running the boiler, sometimes it exploded. The reason being is that hydrogen would entrain itself into the iron boiler, and as it heated up, hydrogen gas was released. So you have oxygen, heat, and hydrogen. That's a recipe for disaster. Hindenburg, this uses the thermite reaction. So thermite reaction and hydrogen gas. Thermite reaction is aluminum plus rust. So if you take aluminum, metal, and rust, you can create thermite reaction, which is very explosive, very big, and creates, as an end product, molten iron. So the thermite reaction started the Hindenburg on fire, and the Hindenburg also had hydrogen gas in it. And this is different than the blimps we have, because the blimps we have helium in them. But that hydrogen gas in the Hindenburg and combined with the thermite led to the massive detonation. So I told you oxidation reduction happens in living things, and many of these reactions. So burning glucose to make the motion in our bodies and any sort of energetic process. Making glucose, that's C6H12O6 plus oxygen, makes carbon dioxide and water. So glucose is oxidized. How do you know? Well, you're adding oxygen to it. See, you're adding 6 oxygens to glucose. You're literally adding oxygen to it, so it's oxidized. and photosynthesis is reduction. So then photosynthesis is carbon dioxide and water being reduced to form sugar. And all the oxygen here on Earth is made by plants, mostly algae. Algae are the ones that produces about 80%. Not trees. A lot of people think trees produce the oxygen on the planet. Trees don't really produce that much. Algae is what makes the oxygen here on Earth. And so permanent waves. If you like to see the curly hair, so ladies or some gentlemen, I assume, you can curl your hair. How do you curl your hair? Well, you take a curling iron and then you twirl your hair up. I don't have enough hair to do this, of course. You twirl your hair up in the curling iron and you let it go and your hair is in the curling. What are you doing when you're curling your hair? You're removing water. You're removing water and you're getting the hair to stick together. Then when your hair gets wet, it goes back to being straight. Likewise, if you have curly hair and you straighten it, once it gets wet, it goes back to being curly. Well, you can do this by taking thioglycolic acid. That's that stuff that smells really bad, and you can smell it every time you walk by a salon. You take the thioglycolic acid, sometimes ammonium thioglycolate is used as well. This reduces proteins in your hair, breaking the bonds. It adds hydrogen to them. The hair is wrapped in desired shape, curly or straight, whatever it is that you want. And then a neutralizer, which is really an oxidizer, then oxidizes the proteins and then reforms the bonds. So that's how permanent waves work.